Okay, the guy. I'm going to talk more about chemical degradation, and I'm going to combine chemical degradation, bacterial resistance, and extended spectrum. Let me talk about them at once. The structure of natural penicillin, which is benzyl penicillin. Remember, for benzyl penicillin, this is the benzyl group attached at R group. So at R group, we have a benzyl penicillin. We have a benzyl group. This is the benzyl penicillin. Or PNG. This benzyl penicillin is the natural penicillin, and it was found that this penicillin was mainly acting on gram-positive bacteria. Also, it was labile to it is acid labile, meaning that it is degraded by the acid. That's the chemical degradation. Also, it is inactivated by those bacteria which produce beta-lactamases, those gram-positive bacteria, for example, Staphylococcus aureus, and those gram-negative bacilli which produce penicilliases. So, inactivated by penicilliases or beta-lactamases. You can call them beta-lactamases. So, meaning that this benzyl penicillin, the natural penicillin, cannot be taken orally because of the acidity of the stomach, meaning it is parenteral. It is parenteral, cannot be taken orally because it is unstable. So they had to make other penicillins which can resist the acidity of the stomach, which can be acting on also gram-negative bacteria. It is acting on gram-positive because of this benzyl group, which is highly lipophilic. Remember, the gram-negative bacteria, they have outer membrane, which is highly electrophilic, which is highly hydrophilic because of the presence of the lipopolysaccharides. Those lipopolysaccharides, they make the outer membrane more hydrophilic, meaning that the lipophilic drugs, they are not easily passing through that membrane. So gram-negative bacteria, they have the outer lipopolysaccharides, and the polymers allow only the hydrophilic drugs to penetrate through. So in benzyl penicillin, it had to be modified. This amide group is the functional group at the side chain. It's the functional group. So the first carbon on this amide group, it's the alpha carbon. Use blue. This carbon is the alpha carbon. This carbon. So it's very essential. That carbon is very essential in the structure of penicillins. If we modify this alpha carbon and put a highly nucleophilic atoms or electron withdrawing groups, we are changing the activity there. So remember, we have, when we talk about the bacterial, chemical degradation, let's begin with the chemical degradation, this acid rabiate. Meaning that if we put an atom which prevent the presence of these electrons here to attack this ring, remember we saw the mechanism that it is the oxygen which attack this carbon. So if we make these electrons unavailable for attack, meaning we are making this penicillin what? Acid stable. So that mechanism of acid instability won't occur, because if we put substituent here which prevent these ones electrons being available, we are making it stable. For example, let's see acid stable penicillins. Acid stable penicillins, for example, pen G, pen V. Penicillin V is acid stable. The structure of penicillin V, instead of benzyl penicillin, it is a methoxyphenyl penicillin now. So it has this group. It has this group at the R. So this group, okay, we do this. Then this is the amine. So that's the structure of pen V, meaning that this oxygen will make these electrons unavailable for attack here. Because you saw the mechanism that it was this one attacking the acid, then taking this bond electrons, then this one attack here. But if we put electron withdrawing group here at the alpha carbon, because this is the alpha carbon, now it is attached to oxygen, meaning that these ones, they won't be available to do this mechanism. So one is NV. So again, for example, if we put at alpha carbon amino group, for example in amoxicillin, what else? Amoxicillin, ampicillin, those are highly electronegative groups. So in amoxicillin, here at alpha carbon of the pen G, there is amine group. Is this amine group. So here there is a nitrogen with H. So this is the structure of ampicillin. This amino group makes this penicillin stable in acid. So amoxicillin is just here. Amoxicillin, this one should have OH instead of hydrogen. In amoxicillin it is hydroxyl group. So if the alpha group is part of the ring structure, either phenyl or naphthyl group, or can be heterocyclic. If this alpha carbon is part of the ring, that penicillin will be stable against beta-lactamases. It won't be degraded. For example, for the bacterial resistant penicillin, they are not degraded by the beta-lactamases. Examples, we shall have the dicloxacillin, cloxacillin, methicillin, methicillin, procloxacillin, nafucillin. So those penicillins are not degraded by the beta-lactamase because the alpha carbon is part of the ring structure. This alpha carbon. Let's take an example of dicloxacillin. It has isoxazole, which is isoxazole here. So dicloxacillin means here we have a chlorine, here we have a chlorine. So this alpha carbon, now it's here, it's part of the ring, that alpha carbon. Then this part is the amide group, then A, H, CO2, H. So this is the alpha carbon. This is the alpha carbon now, because this is the functional group. Now the first carbon is the alpha carbon. So all those penicillins, when the alpha carbon is part of the ring structure, they are resistant to beta-lactamases. And this substituent is very bulky because of the addition of these substituents again. These substituents. So those groups where they have a bulk group and the alpha carbon is part of the ring structure, they are stable to beta-lactamases. Another example for methicillin. Methicillin has this structure. So the alpha carbon is part of the ring structure. Now here we have now the amide group comes. So that's the structure of methicillin. So whenever you see the alpha group is part of the ring structure, those penicillins are resistant to penicillins. Then they are resistant to penicellases. And so these penicillins, they can act now on those bacteria which are penicillin resistant or penicillase producing bacteria. But because of the substituents, it's very bulky, and these substituents are highly lipophilic. These bacteria will act on gram-positives, which are penicillin resistant. For example, Staphylococcus aureus, that is aureus. So they are good for this bacteria. This bacteria is beta-lactamase producing bacteria. So these ones, because this side chain is highly lipophilic, it's bulky, cannot penetrate easily the gram-negative membrane. So it is resistant to penicellases, but it's for gram-positive bacteria which produce penicellases, because gram-negatives, it can't penetrate easily. This is very bulky and highly lipophilic. Now we have this one is done. Then inactivation by penicillins is also done. So how can we extend the activity, extend the spectrum, so that this penicillin can also act on gram-negative bacteria? How can it be done? Again, we shall alter the alpha carbon. So let's see. Extended spectrum. So for extended spectrum, we use groups which are polar or ionizable groups. These groups are added at the alpha carbon. Why alpha carbon? Because this alpha carbon is nearer to this part, the amide group. And this amide group, of course, this alpha carbon again is nearer to this beta-lactam ring, than other parts. So if we alter this alpha carbon and we put substitutes like amine group or amine group, then carboxyl group, we are increasing the activity of these penicillins against gram-negative bacteria. So meaning that, for example, ampicillin is it is targeting both gram-positives and gram-negative, because we are leaving the hydrophilic part, but we are leaving the hydrophobic part or lipophilic part, but we are adding the hydrophilic part, meaning that these penicillins will act on both gram-positives and gram-negatives. Ampicillin, amoxicillin, carboxypenicillins, penicillins like iridopenicillins. For example, ampicillin, here at alpha carbon there is amine group. It's the same structure of benzyl penicillin, but here there is amine group. Amoxicillin, there is amine group, then just there is OH also here. Carboxypenicillins, for example, this one we have the ticagrelin, we have carbenicillin. Carbenicillin, it has the carboxyl group. These two, they have a carboxyl group here, if you look at their structure. Now, for iridopenicillins, also, they have let's take examples for iridopenicillins. Iridopenicillin, for example, azilocillin, they are derivatives of ampicillin. They are derivatives of ampicillin. So in ampicillin, this is amino group. Then it was altered to form uridopenicillins. For example, aziloceline, it is now this is amide group. This is a heterocyclic ring. So these groups, so uridopenicillins are not stable in acid, but they are broad spectrum or extended spectrum, because now this group, after entering the bacteria in the periplasmic space, it will not be easily pumped out. It will not be easily pumped out. It will form bonds with the receptor sites there in periplasmic space, meaning that bacteria like Pseudomonas aeruginosa, can be targeted by these uridopenicillins. So for this is aziloceline. For meziloceline, here there is it was substituted here with the sulfathiol group, then with a CH3 here. One was substituted with this group for meziloceline. Now this is meziloceline. Just here. So these uridopenicillin, they can target those penicillin resistant bacteria because they are not easily pumped out and they can easily penetrate the membrane of those gram-negative bacteria. Then more on the isoxazoyl penicillins, those which have this functional group, the isoxazo. Okay. Those ampicillin, no, those cloxacillin, oxacillin, dicloxacillin. So this group is highly electron withdrawing. So these ones, they are broad spectrum, they are not broad spectrum, but they are acid stable because this one will make the electron here, electrons unavailable for attack by the acid. So they are also stable in acidic pH. Those cloxacillin, dicloxacillin, oxacillin, fluoxacillin, those penicillin. Then, meaning that this one was also extended. Meaning that we have talked about the bacterial resistance, chemical degradation, and the extended spectrum. Now, for protein binding, those penicillins which are highly lipophilic, they bind easily to the plasma proteins, albumin. For example, basal penicillin is highly protein binding because it is lipophilic. So most of those penicillins which are targeting most gram positives, they are highly lipophilic than those ones which are targeting both gram positive and gram negative. So highly binding penicillins we shall have the PNG, then those isoxazoyl penicillins which have the isoxazoyl group, the ampicillin, dicloxacillin, those ones which have the isoxazoyl ring. Ampicillin is one part. which have this one, this ring, that's oxazoline. They are highly protein binding than ampicillin, amoxicillin, and these other penicillins. So for acid stability, iridopenicillins are less acid stable. They are not stable in acid because the amide group was altered, meaning that these electrons will be available for attack. So iridopenicillins are not stable in acidic pH. Then carboxypenicillin is also unstable for it's unstable in acid. Why? Because the carboxyl group is okay, we shall have decarboxylation in acidic pH. So this group will not be available, meaning that here we shall have like benzylpenicillin, which is acid unstable, or which is acid labile. The carboxyl group for carboxypenicillin will be cleaved. So we shall have decarboxylation in acidic pH. So this one is done. Now, allergy to penicillin is due to the reaction of this group, the amide group of the beta-lactam, with the proteins. So this ring, the amide group of the beta-lactam ring will react with the proteins, with the amino groups of the proteins. So the amide groups of the proteins reacting with this part, it's the one responsible for the allergy. Now, when it comes to penicillin salts and suspensions, penicillin salts, then suspensions. So if we form salts, for example, sodium penicillin, meaning that we are using this group instead of hydrogen, we put a salt, which is sodium. We put sodium to make it a salt, meaning that for salts, we are making this part highly hydrophilic. So they are highly water soluble. Meaning that most of them, or all of them, they shall be used for parenteral use. Then if we make suspensions, these ones they'll increase the duration of action, meaning that little will be released. For example, penicillin G, benzathine. Then pen G, procaine. Meaning you add the penicillin and procaine. These two, they are unreactive, or they can't form solution, meaning that you have this one insoluble in this one, or this one insoluble in this one. So they don't form solutions, meaning that little will be released at a time than the salts. So these ones are used for controlled release or slow release. These ones for fast acting because they are highly soluble. They will solubilize easily in the plasma such that they do the activity. Then when it comes to beta-lactamase inhibitors, for inhibitors of beta-lactamases, these ones, they prevent degradation of penicillins. They inhibit those beta-lactamases. So, for example, we shall have the sulbactam, shall have the clavulanic acid and the tazobactam. So, these inhibitors, they are given together with penicillins because they highly inhibit they have high potency at inhibiting the beta-lactamases, but they have low activity for destroying those bacteria. Because of that, they will be given with penicillin so that they inhibit and then the penicillin does the activity. Because for them, they have little activity against the bacteria, but they can inhibit the beta-lactamases. For example, this clavulanic acid can be given with amoxicillin. So this one is marketed in the brand name of augmentin. Then we can have sulbactam. This sulbactam with ampicillin in the fixed dose. So they are fixed doses, the beta-lactamase inhibitors and the penicillin. We can have tazobactam with piperacillin or piperacillin. So this piperacillin is uridopenicillin. So uridopenicillin, which is the derivative of the ampicillins. So sulbactam and ampicillin, they are marketed in the brand name of Unacin or Unacin. Then for tazobactam and piperacillin, they are there in Zosine brand names. So that's all I had for you guys. Same get the guy. Please subscribe, follow, like, comment. I'll be happy. I'll bring more.